All right, welcome back. Hope you guys had a good Thanksgiving break. Anybody eat too much turkey? All right, good. Anybody still eating too much turkey? All right. So I'm from the South. So when I go home for Thanksgiving, it's down to Atlanta. And in the South, it doesn't count as Thanksgiving unless there's a pecan pie around. And I don't know if you've ever seen how you make pecan pie. You take a few pecans and you add some sugar, and then you melt that sugar into sugar, and then you add some sugar. All right, you've had one. Okay, so anyway, I had my pecan pie, or as we call it in the South, pecan pie. All right, there's an error in your text that I need to let you know about. Oh, I guess I should also tell you, you may have noticed that I also caught a cold while traveling, so my voice is going to be kind of weak today. So I'll just ask for your cooperation in keeping the background noise to a minimum. That means try not to chat to your neighbor unless you can do it silently. All right. Yeah, sign language is OK. All right. So there's an error in your text. Now, it's in the context of talking about the direction of changing magnetic fields. So we're entering chapter 23. It's going to be about the effects of changing magnetic fields. And I just want to alert you, if you haven't already seen this error in your text, you'll see there's a place that says from this form, you can see that the direction of dB by dt is the same as the direction of minus delta B. That's not right. These guys are actually in the same direction. So delta B is in the same direction as dB when you convert it into a derivative. So this is what it should read. There should be a minus sign there. And always remember that delta, whatever delta is always final minus initial. Delta is final minus initial. So if you didn't get to that part in the text yet, keep in mind there's a minus sign error there. All right, last time we talked about Gauss's law and the magnetic Gauss's law and Ampere's law. Now, Gauss's law, all right, I should skip forward to the equations and show you. Gauss's law here for electricity told us that if I take a closed surface, all right, I have to remind you what's the difference between a closed surface and an open surface. Has anybody ever played with bubbles as a kid? Like, you know, you get the little bubble wand and you blow the bubbles out, okay? That tells you the difference between open surfaces and closed surfaces. When you go like this and you make the bubbles are closed surfaces. Okay, when you dip the wand into the bubble solution and you just have the film on the wand, that's an open surface. A closed surface is something that has an inside and an outside. A bubble has an inside and an outside. When you dip the wand and you just get a soap film, there's no inside or outside. It's just it's because it's an open surface, okay? So Gauss's law was about closed surfaces, and it told us that if I take any closed surface like a bubble, and I measure the net electric field poking through that surface and add that all up times the area involved so that I get a total electric flux, that tells me how much charge is enclosed inside that bubble. That was Gauss's law. We also talked about Gauss's law for magnetism. Gauss's law for magnetism looks similar on the left-hand side. Okay, the left-hand side was this flux integral, right? We took a closed surface. That's what the circle means on the integral. It means take a closed surface. We took a closed surface, measured the electric field perpendicular to that surface everywhere, and added that up times the area. Okay, we can do the same thing for magnetic fields. Take another closed surface, circle means closed surface, and add up the magnetic field poking through that, and we always found it was 0, which was kind of disappointing. But what it means is that we don't have any magnetic charges, okay? So we have electric charges, all right? But there's no such thing as a magnetic charge, at least not that we've found yet. Remember, I have my friend Dr. Bob was searching for a magnetic monopole, never found one. Maybe you will. Okay? So if you found a magnetic monopole, we'd have to update this. But for now, no one's ever found one, and Gauss's law for magnetism says that the net magnetic flux through a closed surface is 0. So far, these are the rest of the equations as well. So the equations we're talking about are Maxwell's equations. It's a set of 4 equations that tell you everything you could possibly need to know about electric fields and magnetic fields. So 4 equations, and so far, this is what we know. This is for the case of stationary states, okay? So this is for, I shouldn't say stationary states, I'm sorry, steady state. This is the steady state situation. So these are correct and complete for the case where any net charge is stationary and not moving, And if you have a current, if you have a net current, that current is not changing in time. So the key to these equations so far is that you might notice if you look at them, and I'm a theorist, so I like to look at equations. Guys in the back, your conversation is distracting to me. So just switch to sign language or texting each other or writing notes, OK? All right, so the 4 equations here, if we stare at them and you look, you will not see the symbol t, right? There's no time in there yet. OK, so these equations so far are for the steady state situation. Current's not changing with time. Charge is not changing with time. Nothing's basically moving, all right? So these guys aren't changing with time. I know you guys like to flirt during class, but you're distracting, OK? All right. OK, so no time dependence. That's this case. Guys, serious. You don't have to be here, OK? You don't. So if you can't stop talking to each other, then you either need to move or leave the classroom, OK? Thank you. Appreciate that. All right. So no time dependence here. Now, we're going to start adding time dependence, OK? That's what we're going to be doing in this lecture. And in the next lecture, we'll see that there's a way to add time dependence to this equation, and there's a way to add time dependence to this equation. And we'll update those guys, OK? Now, what I want you to think about first, before we add the time dependence, is what these integrals physically mean. So we have here 2 different kinds of integrals, right? So some of these integrals are about flux, and some of these integrals are about circulation or curl. So these guys up here are about flux. So I have electric field flux, and I have magnetic field flux. All these integrals, you'll notice, have closed symbols on them. So if it's about a surface integral, it's a closed surface. If it's a line integral, the E dot dl or the B dot dl, those are about closed loops, and it needs to come back on itself. Okay? So closed surfaces and closed loops, that's what the circles mean. Now, the top 2 equations are about if you have a case where there's an inward or outward pointing field. So the top guy is about the case where I have, say, a point charge, and the point charge makes an electric field that comes out from itself, and those electric field lines splay away from each other. Sometimes we call that a divergence. That's an outward pointing field. Or if it's a negative charge, it's an inward pointing field. So Gauss's law captures that idea that if I have a net flux through a closed surface, that means I have an outward pointing field. Okay? Or I have an inward pointing field, and it means that I put the bubble around the center of that inward or outward pointing field. And these guys at the bottom, those 2, are about curling fields. So the electric field one is about take the line integral of the electric field around a closed loop, all right? And it tells you, OK, is there a circulation there or not? This guy you're familiar with already. In this case, if I drive a current, so let me have a current going through a wire, then the magnetic field that current makes is in loops. It's in little circles or swirls. The magnetic field lines swirl around. And this line integral here captures that swirliness. So that if you have a net B, integral B dot dl around a closed loop, it tells you that that magnetic field lines are swirling around. So these guys are about curly fields. These guys are about inward-outward pointing fields. So these are the configurations we want to think about. Whenever you see those fluxes, the net flux through a closed surface tells you you have an outward pointing field or an inward pointing field. It's this configuration, just like the point charge. If I have a circulation, which is this integral, line integral of B dot dl around a closed loop tells you about the circulation of B around that closed loop. So that's about curly fields or swirls going on, all right? So we take integral B dot dl, and that tells us about the current that's enclosed in that loop. And so right here, I have, for example, a long wire with current coming out of the board. That red dot has current coming out of the board. And you know that the magnetic field lines make concentric circles around that. They're swirling, OK? So closed line integrals are about swirling fields or curly fields. Closed surface integrals are about poking fields. They're poking out or they're poking in. So I know how to get these in these cases. I get a point charge, gives me an outward electric field. A current, a line current, gives me a swirling magnetic field. So far we know how to get the inward-outward electric field and the swirling magnetic field. Okay? There's something really interesting here in that the inward-outward field configuration versus swirling, those are actually orthogonal. Okay? Orthogonal, you've seen this idea before of orthogonal. You know the components of your vector, different components of a vector are orthogonal to each other, right? So you're used to that from Cartesian coordinates where the x component is independent of the y component. and motion along x and motion along y can be broken down into just separate phenomena. In the same way that x and y are independent Cartesian coordinates, the coordinates r and theta are independent in cylindrical coordinates, right? So here, for example, if I have an outward pointing field, its direction is away from the source, right? And that's an independent coordinate from this guy. The magnetic field of the long wire had its direction is theta hat. So it's in this theta hat direction, which is around the center. These are actually orthogonal field configurations. So it means that basically for any field configuration you can give me, I can break up any complicated field configuration you give me. I can express it in terms of inward and outward pointing fields plus swirling fields, okay? Plus there's actually one more configuration I've missed. Can you think of one field configuration that can't be captured by inward, outward, or swirling around? Okay, so there's yeah, all right, we got it in the back here, okay. Yeah, so basically the constant case. Yeah, yeah, absolutely, that merits high fives. So if you have a constant field, could be electric, could be magnetic, but if I say, for example, as he's down in the back like this, take the field lines and just have them run straight up and have them be constant, okay? So if I have a constant electric field everywhere in space and it's all pointing the same direction, it is neither inward, outward, nor is it curling, okay? But if I take those three ideas together, the constant field plus the idea of inward, outward pointing fields plus the idea of curling fields, now any configuration you give me, I can break down into those three components, okay? It's like they're independent field configurations. Okay, now what I'd like to think about though is how can we create the reverse, right? So we have an inward, outward pointing electric field. Can we make a magnetic field that points inward or outward? Right? Well, what's one way to do it? What's one way to make an outward pointing magnetic field? If my friend Dr. Bob found his magnetic monopole, there'd be an outward pointing magnetic field from it. So we actually don't know how to do it because no one's found a magnetic monopole. What about this case though? So we have a curling magnetic field. Can we make an electric field that looks like that curls around? Okay. So what's one of the paradoxes you would run into if you did that? What if you had a curling electric field? What would happen then to the line integral of E dot dl around that closed path? Well, okay, so we expect that the line integral of E dot dl around a closed path is 0, because what we've done so far is relate the line integral of E dot dl to potential differences, right? And so we've said, okay, line integral of E dot dl is minus the voltage. And so that tells me something, it's like we always related potential to height. We said anytime I go a closed loop, a closed hiking path, always come back to the same altitude, right? So if I get a circulating electric field, it's going to violate that, all right? So it turns out that there's going to be a way to do it. It's just that in those cases where we make a circulating electric field, we're going to have to be very careful with that potential equals height analogy is what's going to happen, all right? Okay, so let's see if using all this great physics equipment, we can come up with some curly electric fields. All right. All right. I'm doing this because I like physics equipment. Okay, so what we have here is some solenoids. All right. This guy right here is a solenoid that I can hook up, I can turn on, so I'm going to turn it on. Okay? When it's on, the light bulb will go. The light bulb is just to show you, yes, there's current running through this circuit. So there's current running through the bulb just to show you it's on. And then current runs through this big long solenoid. A solenoid is several sets of concentric, of circular wire loops, and the point of that, guy, is to make a magnetic field, right? This is an electromagnet. It's a rather big electromagnet, but it's an electromagnet. So when I turn the current on like that, there's a magnetic field poking out, coming back in, and there's a very strong magnetic field through the center. And then when I turn it off, there's not, all right? Now, this guy is separate from this. This is also kind of like a solenoid, except it's not hooked up to a power source, okay? So this is several turns of wire, and then it's hooked up to this guy, which is not a power source. It's actually just, yes, okay, it's actually just going to measure for us current, okay? So basically, if this coil will ever get current through it, this needle would deflect. So I'm going to turn this guy on. Remember, when I turn this guy on, there's a strong magnetic field pointing out of its top. It's just a big magnet, all right? So we push this over here, and there was a little transient there. Did you see that? Okay, I'm going to pull it back out. Okay, and again, there's a little transient that happens. Okay, so it's a little bit bigger effect if I actually turn it on or off. So when I turn it on, there's a big effect. When I turn it off, there's a big effect. Okay, on, off. All right. So there's something going on in this guy. This guy can tell, even though it's not hooked up to a power source, this guy can tell whether or not this guy is doing what? Can it tell if this guy's on? Okay, it's on. Are you getting a reading that says it's on? Yeah. Pardon? It can tell if it's changing, right? So right now I've got it on, but there's no deflection. But if I change it, there's a response. If I change it, there's a response. So this guy can tell if the magnetic field coming out of this solenoid is changing or not. Okay, if it's constant, it's not picking it up. So somehow this guy knows. And if this guy knows, right, it's because it's got current running through it. Well, how would it have current running through it? The only way to drive that current would be if there's an electric field that's pushing the current around those wires, right? And in this configuration, that would mean there'd have to be a curling electric field. So we just figured out how to make a curling electric field, okay? The answer is change something, okay? And the thing that we're changing in this case is the magnetic field. So if I change the magnetic field poking through these wires, there's a curling electric field that happens as a result. Do you have any questions so far? Okay. All right. And this is a really fun demo. If I can find, there's the ring. Okay. So what I have here is a bunch of turns of wire. This is just an electromagnet down here. You can see lots and lots of big, thick copper wires, and they're about 10 deep. So this is about 300 turns of wire. And this is just an aluminum ring. The aluminum ring will carry current if there's a curling electric field through it. Okay? So what's kind of fun here is that I've got it situated so that it's centered right on top of the solenoid. And when I turn the solenoid on, this guy is going to feel a changing magnetic field through it. And in response to that changing magnetic field, it should do exactly what this guy did. It should have a curling electric field drive some current through the ring. Right? You ready to see it? OK, I love this demo. Ready? Yes. All right. So something happened. It's always fun to see again. All right. That was cool. All right, we've got another ring here. All right. Bad ring. Try the first ring again, OK? That's more like it. All right, so there's something going on. And I need somebody in the front row to examine the rings for us and tell me what's the difference.
Not a closed loop.
OK. The bad loop, OK, has a flaw, which is that it's not closed. So there's this little gap over here in the ring that didn't work. So what's going on is that as we turn on the electromagnet down here, OK, so we'll turn that on real quick. All right. As that happened, there was a changing magnetic flux through this ring, OK, and then there was a curling electric field, right? The curling electric field drove current because it's a ring. This guy experienced all the same stuff. So when we turned on the magnet, it had a changing magnetic flux through it, drove a curling electric field, yet there's a gap here, so it couldn't carry current. All that happened was that it shifted charges a little bit, charges built up at the edge, and it was stuck, right? So this guy's the one that's fun. Well, let's do it again, because it's fun. Now, what do you think's pushing it up? This guy didn't quite do that, right? So something's pushing this guy up. Yeah, there's a magnetic force on it, OK? So the magnetic forces that we know are QV cross B. That's one of them. OK? Or if you take QV, QV is for a point charge, right? But if I take many, many, many point charges inside of a material, I turn that QV into IDL. So inside of this hunk of material, the force is going to be IDL cross B. So what's going on is that as I turn the magnetic field on, this guy gets current running through it. Well, there's current, which means I can have an IDL cross B. Okay? So if I take current over this way, I crossed into, well, there's a magnetic field coming straight up. Okay, so I crossed into B this way is just going to give me an inward radial force. That's not going to do anything except tend to either contract or expand the ring. So I have to actually consider the fringe field. So the fringe field coming out of the solenoid comes up and splays out. So think of that splaying component. So now I get I crossed into the outward pointing magnetic field. That's going to give me this guy, right? That's going to be what drives it away. And it turns out that a ring will fly away from either side of the solenoid, just like that, which is fun. And yeah, OK. You can see this smoking. I love this. I just want to get it where you can see it. All right. This is liquid nitrogen. All right. So we like liquid nitrogen. All right. Notice I am wearing protective eye coverings. So if I take the ring and soak it in the liquid nitrogen. Yeah. Is there a mic on that? You catching that? It's boiling, right? Because I stuck a warm ring inside of it. Just wait for it to stop boiling, maybe. So what I'm doing is I'm torturing the poor little aluminum ring. OK. But also, I'm cooling it. OK? What happens to the conductivity of the ring as I cool it? Yeah, OK. So the resistivity goes down as I cool it, right? But the conductivity will go up. So this guy, now that it's cold, hopefully, if it works, now that it's cold, it should carry a lot more current. What do you think is going to happen if it carries a lot more current? Yeah, you guys watch out, OK? Just duck if you need to. Yes. Duck, duck. All right, don't pick it up. Thank you. You guys OK? No students were harmed in the making of this. OK, lecture. Yes, that was cool, huh? OK, so the point of showing you that was that, remember when we talked about how the resistivity changes as a function of temperature? Now you've seen it yourself, right? When it's cool, you want to see it again, I can tell. They're like, quit talking, just dip the ring in again. OK, sure. OK, pick up that sound. That's liquid nitrogen boiling. All right. All right, ready? I don't want to catch it, so you guys just watch out, OK? And don't touch the ring. Oh, good. It came back on my side. All right. Good job, ring. All right. Everybody give a hand to the ring, because it's been through quite the ringer today. All right. Good job, little ring. So, OK, that was a lot of physics. But back to our point, OK? Our point is that we've found out that we can make curly electric fields, OK? We just did it in a couple of different ways. Well, it's all the same way, right? We're taking a changing magnetic field. So a changing magnetic field causes a curling electric field. So what we do is we're changing the magnetic flux through that ring. That's what's going on. So we're going to have to update our Maxwell equations. These were Maxwell equations with no time dependence. There's no t on that slide. Oh, you have a question. Sorry. Yes?
Are you saying that the electric field is curly? Isn't it the shape of the...
Oh, I see. OK. OK, so the question is it really fair to say that the electric field is curling? Isn't it just the loop that's curling? So the reason I know the electric, I got to be careful not to touch it. The reason I know the electric field is also curling is because to carry a net current through this loop would require that there's an electric field here driving current, and an electric field here driving current, an electric field down here driving current, and so forth, all the way around the loop. So I'd have to get an electric field all the way around the loop that's in a circle. So while the current's going, there has to be a curling electric field inside that wire. Yeah, does that help? Good question. Other questions? Good question. All right. So what that really means is that when I turn the solenoid on, there are curly electric field down here no matter what. If there's a ring there, the ring will run current. If there's not a ring there, there's still a curling electric field. OK? That help? Some? OK. Good question. Thank you. So we got to update this, though, because we just figured out that we can make one. So that's not always 0. If there's a time dependent, OK, if there's a flux, a magnetic flux that's changing with time. So if there's a d by dt, change with time, of magnetic flux, then we can cause a curling electric field. So now I need to tell you a little bit more about what that math means. So far, on the left-hand side, all the integrals have circles on them, which means if it's a surface integral, it's a closed surface like a soap bubble. Okay, if it's a line integral, it's a closed loop like a track that you would run on or something like that. This guy on the right does not have a circle, and that's on purpose. So what that's about is, if I have a ring, okay, so the case we need to analyze is we have this curling electric field, which is the line integral of E dot dl around this closed loop. The circle in the integral means closed loop, is equal to minus d by dt integral b dot n dA. But we have to define the area of that loop. Okay, I'm sorry, we have to define the area of the flux on the right-hand side. So here's how you define the area of the flux. Take this loop, dip it into bubble solution, and the film of the bubble, that's the area over which you need to calculate this. So whatever your line integral is on the left, right, your line integral defines a path. Could be a circle like this, could be a crazy loop of something or other, all right? Dip that structure into bubble solution and get a soap film. That soap film tells you this area on the right side that you have to calculate the flux through. Now, because it's a soap film and not a bubble, there's no inside or outside. It's not a closed surface. That's an open surface, okay? So I don't have the circle on it. Do you have any questions about how those relate, right? The guy on the left is like your bubble wand, right? The guy on the right is the soap film on the bubble wand. Questions? All right. So we updated this one so far, all right? Now, we still have more to do. Next week, we're going to correct this guy, and we'll see that next week there's actually a way to also make a contribution from changing electric fluxes as well. That'll be next week. Then once we have all those pieces together, then that will be the entire story. That'll be everything there is possibly to know about electricity and magnetism. All right, so let me go back to something we've done before, but now I want to interpret it in terms of Faraday's law. So Faraday's law was this guy, that if I take the line integral of E dot dl around a closed loop, that's equal to minus d by dt of the magnetic flux through the soap film associated with that loop. So that's Faraday's law. Now we've seen this before. This was a case that we analyzed by a different equation, but it's the same physics. So let me just remind you of what we did before, and then we'll interpret it in terms of the new Faraday's law that we learned today. So we've always had this equation, force is QV cross B, right? F is QV cross B, or in the context of a material, the QV of a point particle turns into IDL inside of a material. So here I have the setup where I have two rods that are conducting. I have a resistor connecting them, and I have this bar that's also connected to both rods. And the bar is something that can slide back and forth. And I have a magnetic field. These blue X's are magnetic field poking into the board. The X's are like the arrows on the tail feathers on an arrow, so the magnetic field's that way. And now if I reach in and grab this bar, it's actually hard to do. If I grab the bar and try to pull it, it's hard. Do you remember when we did the generator demonstration, and we saw that if we turned the hand crank, we could run an LED bulb fairly easily, but we had to work really hard to run an incandescent light bulb? So it really is hard to be moving wires through magnetic fields, okay? And that's a difficult thing. So in this case here, I'm going to reach in, grab that wire, pull it through the magnetic field, and at first, before I touch anything, there's actually no current anywhere, right? Before I touch it, nothing's going on. I grab the bar, start moving the bar. Now, all those charges inside the bar feel the force equals QV cross B, right? So then the electrons are moving with a particular velocity as I move the bar. Then there's that V crossed into B, drives a force this way, all right? And then I get a current going. So now that I'm pulling the bar, now there's a current. Now the current goes into this resistor where the energy dissipates. That's why it's so hard to pull this thing. I try to pull it, and I'm burning energy through the resistor as I do it, okay? So we did this before, and we analyzed it in terms of forces QV cross B, all right? That's what started that current moving. But I can also interpret it in terms of this equation, okay? Can you find how, as I grab this bar and pull the bar to the right, can you tell me what would happen to this equation? Yeah. Yeah, A increases. So I've got this set up so that the magnetic field is constant. But as I grab the bar and pull the bar to the right, the area through that loop will change. And that's what this guy's about. So the line integral of E dot dl through that closed loop depends on minus d by dt of integral B dot nda, where A is defined by the loop itself. So as the loop gets bigger, its area gets bigger. As its area gets bigger, the flux is changing, so I drive a current. So it's what you've learned before, but now in terms of Faraday's law, we have a different way to look at it. Okay, same physics, different language. Do you have a question about that? Any questions? Okay, all right. Here's another case we've seen before that we can also think of in terms of Faraday's law. So if I move a magnet into or out of a loop of wire, I get some current running. So actually, I have a demo about that. So let me turn that on. OK, so this is just a big, well, several turns of wire. OK, so this is several turns of wire here. And here it will tell us if we have current running through the wires. OK, all right. If I hold everything steady, there's nothing interesting. All right. And this is a magnet. OK. So if I move the magnet around, I get stuff going on. OK? All right. So basically, this magnet then, as I move it around, causes currents to flow, which is that situation. So I can also think about that in terms of Faraday's law. Right? In this case, the area is not changing. So what's the piece of the magnetic flux that's changing if the area is not changing? It's the strength of the magnetic field that goes through. If I think of this, of a soap bubble over this, the soap bubble, then I need to think about magnetic field poking through the soap bubble. And that's changing as I move the magnet in or out. OK? All right, now the other thing we should figure out is, all right, I'll hold it still. Now watch which way the needle deflects as I move the magnet towards it, OK? OK, it deflected to the right. Now I'm going to pull it out, and it deflected to the left. So if it goes in, it deflects to the right. If it goes out, it deflects to the left. So that's contained in the equations here, because the direction that this is talking about, well, I'll have to show you the right-hand rule. But there's a right-hand rule associated with how you relate the vectors of that integral here, of the line integral around the loop, to the flux through the surface. But suffice it to say that there is a connection, and I'll show you that soon, that tells you which direction that current was going to run. Right? Do you have any questions so far? Right? Here's something else kind of cool. So watch that needle. And north is roughly that way. OK? So I should be getting a pretty good flux of Earth's magnetic field through here. So watch this. I don't want to move the wires. I'm going to hold the wires still. OK? So as I wave this around, I'm changing the flux of Earth's magnetic field through the loop. And you can see can you guys see in the back the needle responding? OK? All right. So there you go. Another way to detect Earth's magnetic field. If you're without a compass, and yet you have one of these little voltmeters, OK? Yeah, OK. Don't do that. All right. Do you have any questions so far? All right. All right. So both of those can be summed up as the Faraday's law. There's another way to write Faraday's law, which is that we can talk about you have a question here? OK. All right. So there's another way to write Faraday's law. This is Faraday's law. But I can also say that this E dot dl is like EMF, right? The EMF driving the current through a circuit. And this flux, I've just made up a new symbol here, OK? Since this is flux, magnetic flux, Greek symbol phi. Phi stands for flux, OK? So we use phi to denote that flux. And then you can write this law in a slightly smaller form. But they're the same thing. So when you see this, it's that. OK? So it's basically telling you EMF around the loop is equal to minus d by dt of the magnetic flux through the soap film that would cover that loop. Questions so far? OK? Definitely time for an iClicker question. All right. So get out your iClickers. Warm up your clicker fingers. So here's the setup. I got to tell you the setup because it's a little bit, it's not terribly clear from the diagram. So I'm going to have two cases up here of an infinite solenoid. So this is not a solenoid, but pretend it was a solenoid. Okay, so pretend it had coils going all the way around it, right? So the magnetic field coming out of coils of wire is very strong inside, and then if there's an end to the solenoid, the magnetic field has to loop back around. But imagine making an infinite solenoid, right? So if I make this infinite on both sides, and yet I'm running current all the way through it, then I'll get magnetic field inside, but if there's no end to the solenoid, there's no place for the fringe field to come out. So for an infinite solenoid, okay, which we have two infinite solenoids up here. Here, the circle represents a solenoid, and this circle represents a solenoid, and this is the sense of the current. So B is pointing out, okay? So in both of these cases, there's an infinite solenoid like this, and there's a magnetic field pointing out towards you, and it's increasing. So basically, we're turning up the current on this infinite solenoid, right? So, and then we have loops of wire. The big thick lines are loops of wire. So here's a loop of wire, all right? And here's another loop of wire, and they're complicated. But what I want you to think about is EMF around the loop of wire based on changing magnetic flux through the wire. So there's the setup, okay? Which one of those two loops will have current in it? All of them, neither of them, or if only one, which one? All right, so tell me what you're thinking. What do we need to think about to analyze this problem? Yeah, thanks. Okay, so you're arguing that there's no current on either one because, yes, okay, all right. So he's, this is very, I'm glad you brought this up. Okay, so he's saying, look, outside that solenoid, there's no magnetic field. Okay, nothing touching this wire. No magnetic field touches the wire. How in the world could the wire possibly know, right? So the wire can't respond. Excellent line of reasoning. All right, you shaking your head? Do you want to? Is there a counter argument to that? Because that's a really good argument. Okay, that wire is touching no magnetic field. Very weird. All right. Is there a counter argument though? What's the flux? How do I calculate the net flux through the wire? All right. Now you don't have to be intimidated by his line of reasoning. There's more stuff to think about. This is a really solid line of reasoning, but there's more stuff to think about. So how about the flux? How do I calculate the flux? Yeah. Okay. All right. So the first line of reasoning got us that there shouldn't be anything because neither of these wires is touching a magnetic field. How could it possibly know? Yet the equation we have says that it's about the flux through the loop. And so in this case, I do have some flux in here, right? So there is flux in here. I think this is what you're saying. There's flux in here, but it's not through the loop of the wire, so it doesn't count, right? So here, if I go through the entire loop of wire and I go, okay, every place, think of a soap film on that wire, okay? So is the soap film intersecting magnetic field? No, not in here, not in here, not in here, but in here it is. And here the soap film is going to cut through some magnetic field lines. And any place that soap film cuts through some magnetic field lines, that gives me a contribution to the flux. And then as that magnetic field changes, I get a contribution to the flux. So you're arguing that, by golly, I know the wire is not touching the magnetic field. How can it possibly know? And yet, this imaginary soap film is touching the magnetic field lines, and it feels the flux increase, so there must be a response. Okay? This is a classic paradox, okay? Because the two lines of reasoning are getting us different answers. So the answer is, all right, and then again, it's a paradox. The answer is that if we do the actual experiment, though, we will see that the guy on the right actually has current running through it. So even though that wire doesn't touch the magnetic field, its imaginary soap film would touch the magnetic field, and it would have changing flux through the soap film. And yeah, I see people furrowing their brows because this is really weird. And so if you have some deep questions about locality of physics, come talk to me after class, okay? And I'll tell you the resolution to that, because it is a really deep issue. But it is also true that this is the case that has changing magnetic flux through it. So we have to conclude that this guy would have some current running through it as you change the flux. Okay? It's a bit spooky, right? Action at a distance kind of thing, and yet it works. So the answer here is C. Okay? And I'm glad we brought out both sides because this is actually really surprising. But the answer is C. And the difference is basically if I have a loop, so pretend this were my infinite solenoid, okay? So pretend I have some wire around an infinite solenoid, and then this represents a solenoid that's now busted through both walls and it's gone to infinity. If that were the case, I have no way to get this ring off, right? Can't take it that way, that's infinite. Can't take it that way, it's infinite. It's stuck, okay? So it doesn't really matter, right? There's any configuration it has, it's always going to have the same flux through it. So it'll always have the response. Now, if I did this, though, and now I make this solenoid infinite, now there's no way to get the ring on. So it'll never have a flux through it in that case. All right? So very weird, spooky action at a distance, and yet you get action at a distance here. So the answer is C. Choose C if you. All right. So again, this was Faraday's law. It told us that if I have a closed loop, no matter what shape, then the EMF is defined as the closed line integral of E dot dl. Okay, same thing. And that EMF then it can be caused by changing magnetic flux through the soap film. Okay, so any shape wire, dip it in bubble solution, it makes a soap film. If there's any magnetic field lines poking that imaginary soap film, which is here, then if there's any change in that magnetic flux, you'll get an EMF. All right? Questions about that? Okay, now I need to tell you the direction. So let me skip ahead a little bit and tell you the direction of the curling field. Right? What we saw before was that there is a definite direction to this thing, right? So when I had this loop of wire and I brought the magnet toward it, it deflected one way. When I pulled the magnet away, it deflected the other way. So we need to figure out if increasing flux drives current this way or if increasing flux drives it that way. All right? So here's how to figure that out. And look at the top left example. All right? And this is the place where in the text of your book it had a little sign error, so don't let that confuse you. That was my announcement on the first slide. But in the top left example here, what we have is we have magnetic field pointing out towards you, and magnetic field is going to be pointing out towards you and increasing. So it's going up. Question is, which way does the curling electric field go? So here's how you can look at it. B is increasing this way. Point your right thumb in the other direction, and then your fingers curl in the direction of the curling electric field. Okay? So magnetic field's coming out this way and increasing. So delta B is out towards you. Delta B is positive. Okay? But I have to point my fingers the other direction. Flip them over. Minus dB by dt is end of the page. Then my fingers curl around in the direction of the curling electric field. Okay? That is the right-hand rule. I went through that a little bit fast because personally I think this is confusing, all right? You're going to get practice with this on your homework, but let me tell you, in my opinion, an easier way to remember it, okay? So here's the easier way to remember it, okay? If you've learned Lenz's rule before, then you know how this should go if you had a loop of wire present, okay? Remember, whether or not the loop of wire is present, there's still a curly electric field there, okay? So what I want to think about this magnetic field increasing out towards you, but I'm going to put a loop of wire around it, okay? The loop of wire, Lenz's rule, is that the loop of wire tends to oppose changes in the magnetic flux through it. So think of the loop of the wire and the soap film over it, and the flux through that soap film, it doesn't like changes in it, so it tends to oppose it. So the loop of wire will spontaneously generate some current so as to oppose that change, okay? So let's think how that would go. So magnetic field's out towards you and increasing, all right? The wire here, Lenz's law, would tend to oppose that change. If I run a current this direction, okay, if current's going that direction and I point my thumb along the current, then the magnetic field would be pointing in, the magnetic field that the wire generates. So the wire tends to make a magnetic field that opposes changes in its flux. I think that's a quicker way to remember all this if you know Lenz's law. And then the direction of that current has to be the same as the direction of the curling electric field. Okay, do you have any questions about that? Either way you want to work it out is fine and we'll get you the same answer. I just find this one easier to remember than that one. Okay? All right, and we're done for today. I'll see you on Wednesday.